Hi, so thanks to everyone for coming. And before I start talking about math, I wanted to say that you can download these slides. They're on my webpage. You can also scan this QR code. I did this to help users of assistive technology, although really anyone can download the slides. Also, if you're watching this on Zoom, one of my employees is live captioning this. But anyway, so my title is pretty long, and the goal of my talk is to explain my title. So the first word is universality, and most of you already know it. This is universality in the context of the central limit theorem. And you'll notice it has 1/2 scaling exponent, and the limit is the normal distribution. I mostly made this slide for my undergraduate students who are tuning in on Zoom. So I'll move on to the next slide. What I actually want to talk about more is the Kardar Parisi Zhang equation. So this models randomly growing surfaces. The equation is, I wrote right there. So relaxation means that big bumps get smoothed out. So on this first image here, you know from calculus 1 that at a maximum of a function, the second derivative is negative. So if you add the second derivative, that decreases the function. Lateral growth means that the surface grows perpendicularly. So this term was derived using Pythagoras' theorem. And this is our right triangle in the second image here. And space-time white noise adds randomness to it. A priori.
Question?
Sorry, yes.
You say non-rigorously, so there is something more fundamental, apparently. What is it?
You mean what? So the question is
non-rigorous? You say non-rigorously, so there is something else that is more fundamental.
Oh, yes. I'm going to explain non-rigorously on this next slide. So yeah, the question was about why it's non-rigorous, and my next paragraph is about why it's non-rigorous. So good question. Yeah, so a priori, it's not mathematically well-defined, and that's because of this nonlinear term. So the derivative of space-time white noise you can interpret as a distribution. Squaring a distribution doesn't really make sense in general. So that's why it's non-rigorous based on just what I wrote there. And I should say there's been a lot of research making this rigorous. For example, Martin Heyer and other people who I thought would be in this room. Anyway, yeah, but anyway, so even though it's non-rigorous, despite that, Kardar Parisi Zhang used renormalization group arguments, and they predicted a 1/3 scaling limit. So what I'm going to consider, or one thing I'm going to consider, is a discretization of the KPZ equation. So this is called ASEP, which Leo and others have already talked about this week. I just want to remind you about its height function. So above a non-particle is a down-right path, and above a particle is an upright path. And notation is that Q is the asymmetry parameter. And the model is much harder to study when Q is not equal to 1, as most of you already know. The next slide is an animation I made. So we start with step initial conditions. And for step initial conditions, it starts in this V shape right there. And as it evolves, it turns into this parabola. But due to the randomness, there's fluctuations around the parabola. So it's a little bit jagged. So some fun trivia about this animation. This is actually 250 consecutive images. So one of my accessibility checkers wanted me to put alternative text on 250 images, which I did not do. OK, I'll stop before it goes to 250 and go on to the next slide. All right, so what are these fluctuations? Yeah, you've seen this before. So it's been known for about 15 years that fluctuations of ASEP are the Tracy Widom distribution. Here's some simulations that I made. I did this with the help of our supercomputer. So Texas isn't just cows. It's cows and a supercomputer, yes. I guess people who know me know my jokes are predictable. So thank you, Evgeny. It's okay. Yeah. So there's another model in the KPZ universality class, which you've seen. This is the stochastic 6 vertex model. So Leo introduced this on Monday, and a few other people have talked about it. I just wanted to remind you that it has 2 parameters, B1 and B2, and only 1 asymmetry parameter. The next couple of slides Leo also already talked about. So I'll skip this because you've seen it already. Yeah, I'll skip this as well. So here, step initial conditions mean that particles come in from the left, but no particles come in from the bottom. And Pramit already discussed this on Tuesday, and I'm actually pretty sure we stole the same image from Leo. So there's a densely packed region here on the left and an empty region on the right. And in between, there's some randomness. And a priori, it might be hard to guess what the randomness is. But as you know from Leo's talk, there's a degeneration to the asymmetric simple exclusion process, which is basically this slide. Yeah, so there's a degeneration to ASEP, so they're in the same universality class, namely the KPZ universality class. And as you've already heard, there's Tracy Widom fluctuations. Here's some simulations. So this would have taken about 5 months on my computer, but it took only 4 days on the supercomputer. OK, so.
What are you simulating on your computer?
Oh, the question was what I'm simulating. So this is the, yeah, I should have said. This is the height function, the rescaled height function of the stochastic 6 vertex model.
At some particular point.
Yes, at this, so at the point 400,000, 400,000. So, yeah, that's a typo. You're the first person to ever point out that that was a typo, yes. But yeah, so time is 400,000, and I picked x as 400,000 just to make it easy. All right, good. So someone's paying very close attention to my slides. OK, so that was some review, the first 8 minutes. So I will go on to explaining the next word in my title, which is dynamic. So for dynamic models, there's a dynamic parameter alpha, which is a positive real number. And what this parameter does is that it interpolates the process between Q and Q inverse. So you don't have to read these jump rates too carefully. They're possibly too small to read anyway. But when alpha is 0, these jump rates are 1 on the left here and Q on the right. And when alpha goes to infinity, the jump rates are reversed, so they are Q and 1. So what happens is that as the height function increases, the asymmetry reverses, so then the height function gets pushed back down. We'll see it on the next slide with an animation. So this is an animation of dynamic ASEP with step initial condition. So there's not a lot going on at the moment in this slide because the particles are not getting very far. OK, and there's also a dynamic version of the stochastic 6 vertex model. So we have this parameter alpha. And alpha interpolates between a stochastic 6 vertex model with parameter q. So there's q. And as alpha goes to infinity, it'll turn into a stochastic 6 vertex model with parameter q inverse.
I'm sorry, Jeff. In
Yes.
this formulation, what is the difference between just replacing V2 or just renaming V2?
Like you say
Sorry,
that's what you're doing.
I didn't hear the question.
So if you just rename B2, then this is back to the usual stochastic six vertex, right?
If you, the question was if you just renamed the B2.
Yeah, you just rename B2 into B2 times Q squared minus alpha 1 minus alpha.
Oh, the question was about renaming this parameter to B2, and the next slide is going to address that because, yeah. Yeah, so, so the dynamic stochastic six vertex model is similar to dynamic ASEP in the sense that the parameter alpha changes over time. So that's really the main point, that alpha changes. It's not just a fixed thing. So hopefully that answers Vidim's question, which...
I'm confused. What is time and what is space?
Oh, yeah, I'm sorry. This is one of the slides I skipped. So you view time, you can view time as the upward direction and space as the horizontal direction.
And downsides, given one row, alpha will be the same value for that row and will be different on the next row.
Yes, so the question was how alpha changes values. So I'll explain right now how the value alpha changes. Yeah. Good questions. Yeah, so yeah, you can ignore that I wrote over time. It just changes by rows and columns. So alpha is multiplied by q squared every time you go up and you cross a line, or you go right and cross no line. And in contrast, it's divided by q squared if you go up and cross no line and go right and cross a line. So that's how alpha changes. OK. So I should have put on an earlier slide that these models were studied and introduced earlier by Alexei Borodin, my PhD advisor, and Omar Agarwal. They also proved that for certain symmetric cases, the height function has t to the 1/4 scaling, and the limit ends up being non-deterministic. There's also work by, excuse me, Ivan Corwin, my postdoc advisor, Permeet, and Konstantin Matetsky. They showed a stochastic PDE limit. So as far as I know, there weren't even any conjectures for the fluctuations of asymmetric dynamic models. OK, so with that as set up, I'll go to my main result. My main result being fluctuations for the asymmetric dynamic models. And so there's a typo here. So where it says +0, it should be is finite. So this result says that the dynamic stochastic six vertex model, it will either has fluctuations which are Tracy Widom asymptotics. Otherwise, it's exponentially vanishing fluctuations. And in case you're wondering, exponentially vanishing fluctuations occur in the usual stochastic six vertex model when q is bigger than 1. So maybe you noticed that I technically never required q to be less than 1. And this condition here about alpha is a technical condition. And I wrote this paper with Zhengye Zhao, who's at IPAM. So she graduated, and I feel like she should move on to she should move on to work with her postdoc advisor at USC. Sorry, Evgeny. All right. Yeah, so anyway, why was I considering the case when q is greater than 1? So that'll make more sense when I talk about dynamic ASEP. So for a dynamic ASEP, the fluctuations are Tracy Widom, and that's if q is less than 1, or it's finitely bounded fluctuations. And so these are either the fluctuations of the non-dynamic model with q bigger than 1, or the fluctuations of the non-dynamic model with q less than 1.
Question. So the alpha is always assumed to be just a function of t.
You can take it, yeah, so the question was about alpha's dependence on t. So you could take alpha to be fixed, and then this goes to 0. You can also extend it slightly by letting it grow with t a little bit. And I should have said in relation to Rick's question that t is basically the vertical, the y-axis.
But you fix it in the beginning and then you run the dynamics. The alpha is some fixed function of t.
Yeah, the alpha is some fixed function of t.
Finitely bounded.
Locally bounded.
Sorry.
What is finitely bounded?
Oh yeah, Prameet's question about finitely. Yes, the question is about finitely bounded. That means with probability 1, the fluctuations are bounded. Yeah, so on the animation where the particles don't get very far, they're never getting anywhere. You might be able to say what that bound is depending on what the value of alpha, but I didn't really try. Okay, so my main claim is that I know universality for dynamic models. So the dynamic models have asymptotics, which are either the same as the asymptotics of the non-dynamic model with asymmetry parameter q, or the non-dynamic model with asymmetry parameter q inverse. Okay, I'll pause here if there are any more questions. Yes.
Functions of alpha do you consider? What's an example of a function?
Something like alpha of t equals like a constant times t, for example. Yeah, I put lim_inf just in case you wanted to have it fluctuate, or between like two values. Like if you wanted alpha t to fluctuate between like 2t and 3t, then you could do that.
So this would be like the RCEP with asymmetry in one direction, slowly transitioning to asymmetry in the other direction.
Yeah, so the question was if it's like ASIP with the asymmetry transitioning from one direction to the other. So the answer is yes. For ASIP, that corresponds to the direction of asymmetry reversing. For the vertex models, they only ever drift in one direction, regardless of how you change Q. So that's, the intuition doesn't quite work the intuition works for ASIP, but that doesn't quite generalize to vertex models. Yeah.
Alpha be like square?
Oh, so yes, the question was if alpha of t could be t squared. So I think, so I think the result would still hold. It's a technical condition. I think what happens is the constants in the law of large numbers and the variance would change. And yeah, I didn't bother doing that yet, but I plan to.
Okay, so the t to the 1/3 would need to be replaced with some other thing. If alpha is like t squared.
Yeah, it's possible depending on how, if alpha is t squared, or maybe it's like t to the 2/3, for example. But yeah, so so I say it's a technical condition. It's not like a trivial thing to get rid of. Right, any other questions? Okay, so that was dynamic processes. So the rest of my talk will be explaining what Drinfel'd twistors are. But before I go into the algebraic part, here's the probabilistic connection. So I'm going to use something called orthogonal polynomial duality. So this first line here could be an entire talk. And in fact, I think Zheng has given an entire talk on this. Reducing the n-particle polynomial to, reducing the n-particle duality to n-particle system is a little bit more standard at this point. Okay, good. The slide changed. All right, so this is about Markov duality. So this is something I've been saying for years. So sorry if it's repetitive. I'm saying it again. So duality is, in general, something of a black art. So this was said by Etheridge, Jensen, Kurt, and myself. What it does is it lets you calculate certain observables of the original process in terms of a simpler process called the dual process. So they should be simpler, not simple, because you could argue how simple any of these processes are. And here's the definition of duality. So you have two different Markov processes, x and y, and you have a duality function. And the function matters in the definition. So the two processes are dual with respect to the function if this identity holds. So what you have here is that you have on the left-hand side, you take d of eta of zeta, and you fix the eta initial conditions. You let eta involve in t. The right-hand side, you fix zeta initial conditions, and you let zeta evolve in t. And duality says that both sides hold for all values of time. And I also wanted to say a trivial duality is if you take d to be a constant function. So in general, finding the duality function is a very important part of the problem. It's slightly less important now that I've developed orthogonal polynomial duality. So I'll elaborate on that point later. There's an equivalent definition of duality for discrete state spaces, which will be helpful later on. And so in this case, duality can be viewed as an intertwining between the generators of the two processes. And this will be helpful because algebra gives a lot of algebra gives a lot of different intertwinings. Okay, so this next slide is just elementary, analysis about orthogonal bases. So naturally, that means I made a typo on it. There should be an h on the right-hand side here. This just says if you have a family of duality functions which are in orthonormal basis, then you can decompose an arbitrary observable onto that basis. So everyone knows that. In the context of this talk, I wanted to say that the basis is indexed by the state space of the dual process. That state space is Y. Okay?
Sorry?
Yes, there's a question.
The condition that these guys be an orthogonal basis for each fixed x or new almost every x?
Yeah, so what you do is, so the question was about fixing.
Oh, yeah, fixed y, I see.
Oh, yeah. The question is about the consensus for what to fix. Yeah, so the basis is indexed by y, so they're functions of x. And so they're functions of x which are orthonormal in the Hilbert space with respect to some measure. I'll say more about the measure later. Yeah. Okay, so here's our duality result. So the duality is between a dynamic model and a non-dynamic model. And before I elaborate more, I should have said on this slide that Alexei Borodin and Ivan Corwin also found a different duality between a dynamic and a non-dynamic model. Later on, I'll give an algebraic reason for why that's true. But anyway, moving on for this slide. So the duality functions are these hypergeometric 3, phi 2 functions, which I should have said are nested product of Q Kravchuk polynomials. Yeah, and these are orthogonal with respect to certain measures called blocking measures. And if you're an expert on interacting particle systems, you know that these are nice measures. I don't have the time or the space to say more about what these measures are. I just want to say that these are nice measures. And also, in part because this is going on YouTube, I forgot to put the names of two other people on here. So two researchers from the Netherlands, Walter Groeneveld and Karel Wagner, I think that's how you pronounce his name. They have duality results for the dynamic ASEP. The duality function is the same, although they don't do asymptotics. Okay, so yeah, yeah, the next slide is intuition for the main theorem about the asymptotics. So this is what the duality function looks like. So it's a product of a linear combination of two terms. Each term happens to be a duality function that I found before. So what happens is that one of these two terms will dominate. And the first term is the duality function for the Q inverse in the non-dynamic case. The second term is the duality function for the non-dynamic model with Q. And I should also note this duality function is related to a paper by Borodin, Kuan, and Sasamoto. And in this paper, the duality function then becomes the nth Q moments. And so before I go on to the rest of my talk, which is all about algebra, are there any questions up to here? OK, cool. I'm pretty much right at the halfway point. So the rest of my talk is about algebra. So the basic idea is that we can associate to the state space of the Markov process a representation of the algebra. And then we interpret the duality relation as a intertwining relationship in the underlying algebra. So let's start with the simplest example of a state space. So there's excuse me. Here there's two lattice sites. So there's four states. So we associate to a particle the vector 1, 0. We associate to a non-particle the vector 0, 1. And then we tensor the two vectors together. So this is a basis of the vector space C2 tensor C2, which is 4-dimensional. And there happen to be 4 states here. OK, so everyone seems OK. So that was just, quote unquote, just a vector space. So what is the algebra? So in this case, it's the Lie algebra SL2 of traceless 2x2 matrices. And this has a basis traditionally denoted E, F, and H. And the action of C2 is just usual matrix multiplication. But in this interpretation, you can give E, F, and H names, which are creation, annihilation, and number. So here, for example, the matrix E creates a particle from a non-particle. Right. And yeah, these vectors on the previous slide. OK, so that was just how SL2 acts on SL2. For multiple lattice sites, we use something called the coproduct. And you'll notice this is symmetric between the left and right tensor products. We also want to be able to create more than one particle. So what you do is you embed the Lie algebra into its universal enveloping algebra, which has the same finite dimensional representations. If you want to define it concretely, the generators are E, F, and H. And as 2x2 matrices, it satisfies these relations. But now we don't have E squared equals 0, and that lets you create multiple particles. So honestly, that was the most basic explanation of universal enveloping algebras of all time. That's all I can say about it in one slide, or I guess half a slide. I do want to note that you extend the coproduct to be a homomorphism of the universal enveloping algebra. OK, so I haven't said anything about Q. So how does the asymmetry parameter Q come into all of this? So this is done with something called Drinfel'd quantum groups. And I will be honest when I say I have no idea how they thought of this. But then again, Drinfel'd is a Fields medalist, and I'm not. But anyway, this goes back to the 1980s. As a historical side tangent, Tom Liggett, who was at UCLA and recently passed away, He told me that back in the day, he and collaborators tried to find duality for asymmetric exclusion processes and weren't able to find it. And I guess part of the reason is that quantum groups didn't exist way back then. But anyway, back to math. So you actually Q-deform the coproduct, not the algebra itself. And you'll notice this is no longer symmetric in the left and right directions. But if you take Q going to 1, you can recover the usual SL2 using L'Hopital's rule on a formal level. OK, so this next slide is a side remark about Lie algebras, or other Lie algebras, I should say. So if you consider so-called, if you consider higher ranked Lie algebras, like SLN plus 1, you get so-called multi-species models. Here are some papers. So I have a funny story about this. Funny in retrospect. It wasn't funny at the time. So in 2015, how's the story go? Right. So in 2015, my son had just been born, and I was in graduate school. So I told my wife I needed to go down to New York City to look for apartments and talk to Ivan Corwin about research I had done, because he told me to look at duality. So I get to Columbia, right? I'm in Ivan's office. I don't know if you've been there. And I'm telling him about my research. Literally 30 seconds in this conversation, he says, you know, Jeff, this looks really familiar. So he pulls up archive. And that exact morning, Blitzky and Schutz had the same result for n equals 2. So after that, I go back home to Boston, and I say to my wife, hey, I know you just watched our newborn by yourself for 3 days, but I need like a week to focus on math because I got scooped. And she was like, yeah, OK, fine. And it was fine, right? But then a year later, I returned the favor to them for general n. But I think Günter Schutz and I are on good terms. We talked to each other in Eindhoven, and he seemed friendly. So everything was fine in the end. This second item, what I want to say is you can give undergraduate research problems by asking them to repeat the same arguments for other Lie algebras. Yeah, I know. Somehow, nobody has ever accepted an offer to look at the type E, the algebra. So Texas A&M has an REU that's been running for 25 years. Yeah, this last paragraph. So I have the first duality result for asymmetric models with open boundary conditions, as well as the second and the third. I don't really want to say much more about it, except that it uses other algebras, such as Schur-Weyl duality with Eck algebras. OK, so to be honest, I mostly told you all that story to give your brain a break from algebra. So we're going to go back into algebra now. So the coproduct is not symmetric, but it is something called almost symmetric. And the more precise terminology is it's almost co-commutative, if that means anything to you. So even though the coproduct is not equal to its reversal, it does intertwine with its reversal using something called the R matrix. And the R matrix satisfies something called the Yang-Baxter equation, which you've seen before this week. I wrote it here symbolically. It's honestly a little bit more helpful to view it as a picture. So here's the picture. So this is a two-dimensional image of or three-dimensional picture, which is never fun for alternative text. But it's OK. I can describe what's going on. So you have 3 lines labeled 1, 2, and 3. And at each intersection, you have an R matrix. And the way I drew this, you multiply the terms from bottom to top. So if you move the middle line over to the left, the equation is the same. So this has physics origins where it's called the quantum inverse scattering method. But it's pretty algebraic at this point in time. Anyway, so this algebra just keeps on going. Right? So I have only introduced one parameter q, right? But the 6-vertex model has 2 parameters, b1 and b2. So the second parameter comes from something called affine Lie algebras. So you take Laurent polynomials in the Lie algebra G, and here C is the central charge, which is actually already mentioned earlier this week. So this then gives you another parameter by letting T act as multiplication by Z. So obviously, there's a lot more to affine Lie algebras than just giving you another parameter in probability. But it does do at least that, give you another parameter. And there's also a spectral dependent version of the Yang-Baxter equation, which I wrote right there. OK, so what about the dynamic what about the dynamic parameter? So there's something called the dynamic Yang-Baxter equation, which I wrote here symbolically. The next slide has it more visually, which is honestly a lot more helpful. I just wanted to recall that H is the number operator. OK, so I'm doing OK on time. OK, so this next slide, the thing I want to convey here is that vertex weights are duality functions. So here we have 3 lines, and I've labeled them 0, I, and I plus 1. And if we move this line to the left as before, the equation's the same. But now what we're doing is interpreting the line labeled as 0 as a duality function. So these are vertex weights. And the lines labeled by I and I plus 1 as the local generator. So this idea was communicated to me by Michael Wheeler, and I gave him credit for it in our paper. OK, I don't think Michael's here right now. Yeah, so I remember the exact date he told me this idea. It was May 2nd, 2017 in New York City. And the reason I remember that is because my wife had just given birth to our second son. So I told her, hey, I know you just gave birth, but you know Michael Wheeler's in town. And she was like, yeah, fine, Jeff, it's fine. And it was totally worth it, by the way. But anyway, moving on. So this gives an algebraic reason for why the dynamic model is dual to the non-dynamic model. So the original process has finitely many particles. And the dual process, sorry, let me start that over. The original process has infinitely many particles, and the dual process has finitely many particles. So here, H is the number operator, so H equals infinity. And if H is infinity, then the generator of the dual process no longer depends on alpha. So this will reduce the non-dynamic model. OK, so that's why. OK, everyone seems OK with that. So I'll go on, finally, to Drinfel'd twisters. So Zhengye Zhao actually knows these better than I do. Okay. So if you have something called a quasi-triangular quasi-Hopf algebra, you can construct solutions to the dynamical Yang-Baxter equation using this Drinfel'd twister. So as long as it satisfies something called the shifted co-cycle condition, yeah, it's a Drinfel'd twister. And to be really honest, I don't have a great way of explaining this to you right now, especially in 10 minutes. You should ask Zhengye because this is actually her idea. I do want to say that this approach ended up being easier than the using the Felder-Varchenko elliptic quantum groups, which is what Alexei Borodin and Amol Agarwal had used. Yeah, and I think I forgot to say on this slide that Zhengye says that the approach is isomorphic somehow, which I've never pressed her on, but it'll give you the same thing. OK, so I have a few more slides left. And I'll probably finish a few minutes early, in part because Leo and Promi and others have covered some things that I was going to cover as background. So this is a very general and algebraic result. So it says that if you start with the quasi-triangular or quasi-Hopf algebra, which satisfies a whole bunch of relationships, which I'm not even going to try to read out to you out loud, then there's a duality relationship. And there's actually good reason for these, there's actually good algebraic reasons for these relationships to hold, which is on the next slide. So the first identity over here is due to the form of the universal R matrix. Yeah, so in case you're wondering, these are, I guess, are the Borel and Cartan subalgebras, the union of those. The second identity is due to a non-trivial automorphism of the Dynkin diagram, if that means anything to you. Based on the looks on your face, it probably doesn't. That's OK. All right. So this is, so far I haven't said anything about how we know that dualities will be orthogonal. And so this single slide could also be an entire talk. So this is based on previous work with Zhengye and Chiara Franceschini. So Chiara was supposed to come here to IPAM, but she apparently got a tenure track job in Italy and wasn't able to get out of teaching. I suspect this paper helped in her tenure track search. Sorry if that sounds like bragging. Young people who collaborate with me usually turn out well. Anyway, I don't want to say too much necessarily, except I'll say that if you use something called the star-Hopf algebra structure of the quantum group, then the star structure is going to produce orthogonality for the duality functions. So we did this for the n species A sub qj. So that's a partial exclusion process. And I want to point out that this method actually doesn't use the Yang-Baxter equation. So you actually don't need integrability. And so one of my dreams is to use get Tracy Widom for non-integrable model. Yes, there's a question?
What are the processes here? Are they both multi-species?
Oh, yes. So the question was if both processes are multi-species. And yes, they're both multi-species models. You could have the dual process only have one species of particle as initial conditions, but then that just reduces to the usual, like not usual, but the single species duality that Carinci, Giardina, Radix, Sasimoto came up with, I guess 10 years ago now. OK. Yeah, so I guess if Zhengye were here, I'd be embarrassing her. But so this, one of the key steps is using the Q-Baker-Campbell-Hausdorff formula. I also wanted to say that Chiara and collaborators came up with something called the inner product method, which to produce orthogonality. And that actually doesn't generalize algebraically. So Zhengye figured out how to use the Q-Baker Campbell-Hausdorff formula. Yeah, so she's very talented. I could not have done this paper without her. OK, so I am actually done now. So thanks for listening.